Hello everyone and welcome to session number 5 of this set of videos created to explore programming applications in reinforced concrete. In this session, we will not use a Maple worksheet, document or workbook. We will use a Maple Maplet that I built from scratch to combine all the beam flexural analysis cases that we have dealt with so far, namely singly reinforced rectangular beams, doubly reinforced rectangular beams, T or L beams carrying positive bending moment, and T or L beams carrying negative bending moments. If we ask Google for the definition of a maplet, we get a Maple Maplet is a custom GUI applet designed within the MapleSoft software, enabling point-and-click interactions with its mathematical engine without requiring knowledge of Maple programming syntax. Maplets typically include windows, buttons, sliders, and text fields, allowing users to visualize plots, perform calculations, and create interactive, focused applications. What this basically means is that the user is not interested in the coding and the programming in the background, and is only interested in generating results, which can be easily done using the Maplet. But in order to create a Maplet, and if we go to the MapleSoft website and search for the tutorial creating a Maplet application, we will find plenty of examples that show how to create user-friendly Maplets, which require an extensive amount of coding. Let us now open our Maplet in Maple. This here is the Maple worksheet that contains all the work required to generate the Maplet. By clicking Enter anywhere within the code, we start our Maplet and our beam cross-section application. As indicated on the main window, this Maplet is designed to perform flexural analysis of reinforced concrete beam cross-sections. You can see on the right side of this Maplet window that we have a help menu, system of units, singly reinforced rectangular beam, doubly reinforced rectangular beam, T or L beam carrying positive moment, T or L beam carrying negative moment. These are the cases that we handled in our previous sessions so far. If we click on the help menu, we will have another screen that shows the 4 different cases that this Maplet is designed to perform analysis for. If you click on each and every one of these cases, you will get an enlarged image so that you can see the parameters involved. For the singly reinforced, this here is the figure that shows all the parameters involved in the analysis of singly reinforced rectangular beam cross sections. If we click on the doubly reinforced, we get the same thing. If we click on the T or L carrying positive bending moment and T or L carrying negative bending moments. This here is the system of units menu, where the user can select to use the standard international system of units, or in short metric, or the United States customer units, or in short English. If the user clicks on United States customer units and clicks on save and close, then everything will be in the United States customer units, capes, feet, inches, and so on. And if the user decides to use the standard international system of units, then everything will be shown in metric units, which are kilonewton, meters, millimeters, and so on. What is next is the most important part of this Maplet, which consists of 4 different kinds of reinforced concrete cross-sectional analyses. First, we have the single reinforced rectangular beam, then the doubly reinforced rectangular beam, T or L beam carrying positive moment, and T or L beam carrying negative moment. When we click on the first one here, single reinforced rectangular beam, a window will appear. In this window, we see 3 columns. In the first column, the user inserts the required input parameters, which are the width of beam, the depth of beam, diameter of bar in the layer farthest from the neutral axis and tension and the numbers of bars there, the diameter of bar in the layer next to it and the number of bars there, concrete cover, diameter of stirrups, compressive strength of concrete, and the yield stress of steel. You can see that these parameters are identical to those that we have inserted in session 1 of this recorded videos. The user can run the analysis by clicking here on Run. Let's say the user by mistake inserts the diameter of bar in the layer farthest to be smaller than the diameter of bar in the layer next to it and clicks on Run. Maple corrects that mistake automatically, indicating that the larger bar should be placed farthest from the neutral axis for the use of the steel to be more efficient. If we click again, you will see that the color will fade, indicating that the analysis is correct this time. The user can modify any of these parameters and click on Run in order to obtain the corresponding results. Let's try here 400. You will see that Maple will produce results indicating that the section is in the transition zone and thus it is not adequate and does not satisfy the ACI code requirements. You can see that in this Maplet, the results are formatted. Every result has its own units presented on the right side of the boxes showing the results. As I promised in previous sessions that I will show you how to format your results in more advanced applications. We can close the singly window from here and go to the doubly reinforced rectangular beam analysis, which will initiate a new window. Again, the user will insert the required input parameters on the left side, while Maple will produce the output parameters in the middle and right side of the screen. We have similar input parameters here: beam width, depth, number and diameter of bars in both layers. We have concrete cover and diameter of stirrup, F sub C prime, and yield stress of steel. Next, we have new parameters, which are the diameter of bar in the compression steel, the number of bars of compression steel, and the number of cycles required to obtain the stress in the compressive steel using the iterative procedure. Again, if the user clicks on Run Analysis, the results will be produced. Let's say the user inserted here diameter of bar in such a way and click Run. Again, Maple will fix the distribution of steel in order to have a more efficient utilization of the steel used. If the user is interested only in the final results, then the user can hide the iterative procedure results. And if the user wants to see the iterations in the iterative procedure, then the user can show iterative procedure results. Again, changing the parameters here will give you different outputs. We can close the double window from this button here and go to the T or L beam carrying positive moment. I'm going to click on it here. This will show a new window. Here, the additional parameters required are the effective width of the flange and the depth of the flange or the thickness of the flange. By clicking on Run Analysis, the user can produce the required results. Note on the right side that this T-beam will be treated as a rectangular beam, as the compression zone shape is rectangular, which indicates that the depth of the compression zone is within the flange. If we change the parameters here such that the flange thickness is lesser and we increase the number of steel bars, then you can see that this section here has been activated for the beam to be treated as a T-shaped compression zone beam. Now the depth of the compression zone is outside the flange, and thus the compression zone is not rectangular and it has to be treated as a T-shaped compression zone or an L-shaped compression zone, depending on the beam that you are trying to analyze. Again, if the user inserts the diameter of bars in a way that is not very efficient, Maple will correct the inserted parameters. Note that this here is a positive bending moment analysis, which means that the steel will be placed within the web at the bottom of the beam. We can close this section by clicking on the close flange section here and open the fourth type of analysis, which is TRL beam carrying negative bending moment. Here the beam can be treated in two different ways. If the steel running from midspan to the support section is taken into consideration, then the beam can be treated as doubly reinforced. But if the steel running from midspan to the support section is disregarded or considered as hangers, then the beam can be analyzed as singly reinforced. By clicking here on the run as singly, the beam is run as singly reinforced. And if we click on the run as doubly, the beam is ran as doubly reinforced. The user here can change the number of cycles from, let's say, 15 to 10 and click on run. To see the results of the iterative procedure, the user needs to activate show iterative procedural results here, where the results of the iterations required to obtain the stress in the compressive steel are shown. If the user is not interested, then the user can hide these iterations, and again the user can switch between doubly and singly by a click of a button. Let's close this window and go back to the main window here and check the system of units. Let's choose the United States customary units and click on Save. Now all the templates that we have seen before will be in terms of the United States customary units. So if we click here on the singly rectangular beam, you will see that all parameters will have units of inches, inches square, Gibbs feet for moment, and KSI for stresses. The same thing for the doubly. Same for TRL, carrying positive moment, and TRL carrying negative bending moment. Therefore, this maplet can treat beams with different system of units and produce the required results. This concludes the session for today. Hopefully you enjoyed watching it, and I hope that we will meet again in the upcoming sessions. Best wishes.